Welcome to the video on the paper Similarity Search with Tensor Core Units by Thomas Ahle and myself, Francesco Silvestri. Let's start by introducing the notion of Tensor Core Units. And to introduce Tensor Core Units, we need to start from deep learning. So we all know that deep learning is now widely used in several application domains, and that deep learning is also a very computationally demanding task. So the research in recent years have been addressing how to improve the performance of deep learning. And one research line has been to design domain-specific hardware accelerators for improving the performance of deep learning. And nowadays we have dozens of commercial hardware accelerators like boards such as Google Tensor Processing Units, the NVIDIA Tensor Core. We have traditional processors with assembly instructions for improving the performance or speeding up deep learning like Intel Dial Boost or the processor Apple Bionic. And we also have very cheap USB sticks that you can just plug in your laptop to speed up your deep learning application, like, for instance, the Intel Neural Computing stick or the Coral USB accelerators. Okay, so the majority of these accelerators has a hardware circuit for small and dense matrix multiplication. Why? Well, because matrix multiplication is one of the most frequent primitive in deep learning. And it also has a very high computational cost, so is the best primitive, the best computational problem to address to improve the performance of deep learning. And it's also very easy to design an hardware circuit for matrix multiplication. So note that these hardware accelerators cannot multiply any matrix. This hardware accelerator can multiply two matrices of fixed and given size. Let's say size square root of m times square root of m. And m is hardware-defined parameters. For instance, in NVIDIA Tensor Core, m is equal to 16 squared, while in the Google Tensor Core unit, m is 256 squared. Well, now using this hardware accelerator, we can multiply two matrices of this size very efficiently in time proportional to the input size, but in sometimes even less, instead of the traditional course, which is m to the 3/2, if you use the classical matrix multiplication algorithm. So we call these hardware accelerators. So these hardware accelerators have a small and dense matrix multiplication circuit. We call them Tensor Core Units. So now the question is, can we extend the application domain of TCUs? So there is life behind deep learning. There are other problems behind deep learning. And since these hardware accelerators exist and we can buy them very quickly, and these accelerators sometimes are very cheap, well, it would be a great idea to use these accelerators for other computation problems. Let's make an historical example. Take graphical processor units, GPUs. So these boards were designed for games, but now they are used for data mining, machine learning, similarity search. And now what we would like to do is to repeat the same with Tensor Core Units. And there are preliminary results in this direction that use TCUs for speeding up prefix sum computations, FFT, and graph problems. What we would like to achieve in this paper is to show that we can speed up similarity search problems using Tensor Core Units. And we start with two primitives of similarity search: dimensionality reduction and similarity join. Before designing and analyzing algorithms for Tensor Core Units, we need a computational model for Tensor Core Units. That is a model where we can study the complexity of our algorithm. And we use a model that appeared as a brief announcement in SPA this year by Dybdahl and Silvestri, which is called the mTau TCU model. So this model is quite simple. It's a standard RAM model where we have one instruction more that allows us to multiply two matrices of size square root of m times square root of m. And the cost of the multiplication of these two matrices is tau. So now m and tau are the two parameters characterizing the model. And in the presentation for simplicity, we assume tau to be big O of m, although in the paper we provide results for general tau. So now with this very simple model, which is a RAM with instruction for matrix multiplication, of dense and fixed size matrix multiplication, well, with this model, we can start designing algorithm for similarity search. So let's start with the Johnson-Lindenstrauss dimensionality reduction, or the JL reduction. So the JL reduction embeds a high-dimensional space R to the D into a low-dimensional space R to the K with low distortion. So, and let's denote with F this embedding. Now, what we have is that if K is at least epsilon to the minus 2 times log 1 over delta, there exists reduction and embedding that for a given vector x, it will serve its norms up to a factor 1 plus minus epsilon, with probability at least 1 minus delta. In other words, for a given vector x in the high dimensional space R to the D, we have that the norm of f of x is between 1 minus epsilon times the norm of x and 1 plus epsilon times the norm of x. So f is a linear map, that is, we can express it as the matrix the product between a matrix M and the vector x, where M is a matrix of size k times d. So now observe that the Johnson-Lindenstrauss reduction is a matrix vector product. So the right term is a vector. So the question now is, how can you exploit an hardware that's been designed for matrix multiplication for the computing matrix vector product? So in general, of course, we cannot exploit and get less than n squared time. But here we will exploit some property of the Johnson-Lindenstrauss reduction and our accelerators. So what we need to do is to find a matrix M that allows us to transform the JL into a sequence of matrix multiplication. And the trick is the following one. So take the matrix M defined as here in the picture. So it's a block diagonal matrix where we have on the diagonal, we have the matrix A repeated several times, and we have zeros otherwise. So A here is a traditional JL matrix of size C times C. And you can construct this matrix A taking your preferred JL construction. So now, this matrix C has a very nice property. So we can reduce the matrix vector product M times X into a matrix times matrix multiplication. Indeed, M times X can be computed as A times the following matrix, x0, x1, dot xd over c minus 1, where here in the right term, the element xi is a vector column representing a segment of of x. So this right term here is a matrix of size c times d over c. And this matrix is basically a representation of vector x. So in this way, we can easily exploit our Tensor Core units because here we have a matrix and we have results showing how to compute matrix multiplication of any size using Tensor Core units. However, it turns out that just having one matrix of a diagonal matrix is not enough to get the desired bounds. So what we actually need to do is to repeat the process a logarithmic number of times using different matrices. Or, say in other words, we need to multiply x with this a matrix M given by the multiplication between a sequence of matrices ml minus 1, ml minus 2, and so on. And each one of these matrices is a diagonal matrix which uses a different block A. So more specifically, when we consider matrices from left to right, we have that the matrices M, I increases, the size of these matrices increases going to the right. At the same time, the size of the block diagonal that we use inside the matrix, so L minus 1, L minus 2, and so on, decreases. So when we consider matrices going to the right, we get larger matrices, but these matrices are also sparse. And since we have these matrices have geometric decreasing as a geometric series, the price of all these matrix multiplication is dominated by the first one, the largest one, which we can compute using the Tensor Core Units. So now the question is, how do we construct this sequence of matrices? Well, we use a recent approach by Ahle and Knudsen that you can find in arXiv from last year. And using this result, and of course the Tensor Core Units, we get this upper bound. So big O of D over K, remember that K is the size of the space where we project, divided by square root of M, plus K squared times a logarithmic term. So in other words, if we ignore the right term here, and we just consider this term here, we have that with Tensor Core Units, we can improve the running time by a factor square root of M with respect to the traditional approach that takes time d times k. Moreover, if our Tensor Core Units is able to multiply matrices, sufficiently large matrices, that is, if k is more than square root of M, well, this approach is also able to speed up, to improve the performance with respect to the approach for dimensionality reduction based on FFT, which takes time proportional to d times log d over log m. So this shows that in principle we can really obtain high gains using Tensor Core Units for dimensionality reduction. Let's now move to the other problem, to the Similarity Join problem. Here we are going to use different techniques. So the problem is the following one. We are given two sets of points P and Q of n points. Two sets of points P and Q of n points. And we want to find all pairs of points P and Q whose distance is below a given threshold R. That is, we want to find all pairs of points, one point in P and one point in Q, whose distance is below the given threshold R. And we call these pairs of points near. So in this paper, we focus on distances that we call the IP distances. That is, all distances that can be computed with an inner product. This class of distances is quite wide and includes well-known distances like the Hamming distance. Indeed, the Hamming distance between two vectors x and y can be computed by the inner product of these two vectors, where the left vector is simple transformation of vector x, and the right vector is a simple transformation of vector y. We also have that IP distances are the Euclidean distance if we ignore the square root, the cosine similarity, and much more. So now you can see that if the distance can be computed with an inner product, well, we can use Tensor Core Units because matrix multiplication is a bunch of inner products. Indeed, if we can use TCUs for efficiently computing IP distances between points in a given set. More specifically, Let's say that X is a matrix representing n vector of d dimensions. Then X times, so here should be times X to the t, give all distances between the m square pairs. So the matrix multiplication between X and its transpose give us all the IP distances. So if without TCUs, this matrix multiplication is quite expensive and it's going to cost us n squared times d. However, if you use tensor core units, we can improve the running time by square root of term square root of m. And we are also going to have these gain, this square root of m gain with LSA, with Similarity Join, as we will see in a few slides. So now with TCUs, we can compute a lot more distances for a given amount of time with respect to the traditional approach where we don't use tensor core units. So we are going to use this trick to speed up the classical similarity join based on locality sensitive hashing, LSH. So LSH is an hash function where the collision probability between 2 points is proportional to their similarity. So 2 very close points are more likely to collide than 2 far points. Let's see now how we can run similarity join TCU. I'm not going to see all the details. Please give a look to the paper for all details. But the high-level idea is the following one. So now, without tensor core, if you use the standard approach, we have to use an LSH where near pairs collide with probability at least 1 over n to the rho, where rho is a parameter given by the LSH. On the other hand, we need far points to collide with probability 1 over n, and we need this term here to be very small in order to not having a lot of distance computations between far points. Now, if you use tensor core units, what does it happen? It happens that we can relax a little bit the collision probability between far points. So it's fine to have collisions, a little more collision between far points. So we ask our LSH to have a collision probability between far points at most square root of m over n. So a factor square root of m larger than the previous one. And as a consequence, we have that the near pairs collide with a slightly higher probability, which is square root of m over n to the rho. So with this new approach, with this second approach, we have 2 things are happening in our algorithm. First, since we have a high probability of collision between far points, we need to compute a lot more distances. But this is not a problem because thanks to tensor core units, we can compute these distances without increasing the running time. At the same time, since we have a higher collision probability between near pairs, we need to use a smaller number of LSH. And this reduces the overall running time of our algorithm. So summarizing, if we compare the 2 approaches, the standard approach using LSH and no TCUs, the running time is n to the rho times this term here. And this term is the number of near pairs. With the proposed approach, we have an improvement because first we divide the overall running time by a factor square root of m. Also, this term here improves by a factor square root of m to the rho. So the overall improvement of our algorithm is square root of m to the 1 plus rho. Okay, so it's time now to summarize. And in this paper, we showed that in principle, it's possible to use deep learning accelerators, the so-called tensor core units, to speed up similarity search. And we have focused on 2 particular primitives, the Johnson-Lindenstrauss dimensionality reduction and similarity join. And we showed that we have a speed up larger than square root of m. Future work, as you have seen, is a theoretical result. And it would be nice now to have an experimental variation of our result, to take these algorithms and run them on real hardware, on, for instance, on the NVIDIA Tesla or in the Google Tensor Core Unit. The second direction is take your preferred similarity search problem and design an algorithm that exploit Tensor Core Units to speed up your problem. So I thank you for watching this video. If you have any question, please join the season session on Wednesday at 3:20 in the afternoon, Central European Standard Time. Otherwise, just write us an email, and these are our two emails. Thank you for your attention, and see you soon.